Hi everyone, my name is Benjamin Kohler. I'm a PhD candidate at the Center for Law and Economics here at ETH. And today I'm going to talk to Berk Ustun about recourse verification. I'm very happy to have with me today Berk Ustun, Assistant Professor at the University of California, San Diego. Berk, you are working on topics within machine learning, reaching from optimization to responsible AI. And I want to talk to you about today about a topic that has really big policy implications in the realm of fairness. Maybe as a start, could you give us a quick summary of the paper and what real-world applications make you think about it?
Yeah. So I suppose like a good starting point for the paper are really these applications that you call like ubiquitous. So these consumer-facing applications where we're using machine learning models. Over like the last 20 years or so, we've kind of built the infrastructure for prediction. And we're using it to automate a lot of decisions that were usually like bureaucratic, simple decisions, but that were important decisions. So lending, hiring, those are one case, but also, for example, public services, like who gets approved for benefits, who is going to be reimbursed for a health insurance claim or a visa processing case. So these are all kind of big, high-risk applications that are currently being regulated in the EU under the AI Act. And there's attention that's being drawn to them also, for example, in the US. And I suppose that as a broad motivation, this is kind of like a double-edged sword. On some sense, you want to really be able to automate these decisions to make these systems work efficiently. Even by automating loans, what you're doing is that you're improving credit access, right? On the flip side, prediction models are imperfect. And they can lead to harm. And when they do, whatever harm that may be, right, you can end up systematically denying someone access to a good. So our paper is really about this effect where I can tell that a prediction model is denying access. And what's happening is, for example, someone like you might be applying for a loan. You're getting denied. That's okay. But usually, there should be a way for you to be able to qualify, right? So if you get denied for a loan, maybe you could increase your income and get qualified again. By nature, there's this blind spot in models where sometimes when you get denied with a fixed prediction. And so we call this effect algorithmic preclusion. And our goal is to try to detect this at a high level. And the broader motivation is really just to try to improve the safety of these models. So it's just one small part of safety, but I think it's important in part of a larger ecosystem of tools that you'd use.
Now you developed this recourse verification test. How did you bring that into practice and what were key challenges in doing so?
Yeah, so our method really starts off from a data set. We will take a look at all of the different input variables in a data set. So these are variables that go into a predictive model that are used to maybe predict whether or not you're going to get a loan. And we start by asking you to specify how you can change each one of these variables and how changing these variables would affect other variables in the model. So for example, if the model is using something like sex, like you can't change that. Maybe your number of dependents or your marital status, you shouldn't have to change that. But something like income, you could change it and you'd probably increase it. Something like the number of credit cards, you could also kind of increase or decrease it. Right? We make it really easy for you to be able to specify these constraints on how each of the variables could be changed and how they would affect other variables in the model. And we do that with software. So we've built kind of this back-end software that's called an action set API, and it just allows you to kind of go into Python and just write it out in clean code. And basically, given any of the inputs to a prediction model and this action set API, what we will do is create kind of a reachable set. And so that is a set of all possible inputs that you could possibly pass into a predictive model. So this is just basically a set of all different points, and each one would be some version of you where you've changed the variables in some way. Given this reachable set, what I can do is take another model and look at its prediction over these inputs. If the prediction changes, that means that you could be assigned a negative prediction or a positive prediction. You could be approved for a loan or denied for a loan. If it doesn't, you could consistently be approved or you could consistently be denied. And so whenever you're consistently denied, that means that the model is kind of precluding you from access. Right? No matter how you change your current variables over the reachable set, you are always going to be assigned a negative prediction.
Interesting. In your paper, you also run experiments. What are the results of these experiments? Do models actually deliver fixed predictions?
Yeah, they do. I think like our big motivation for these experiments was really to try to show that models could assign fixed predictions. And I think stepping back, like an even greater motivation here is just the fact that people don't know about this effect. In some sense, whenever a model is assigning a fixed prediction, you never really find out about it. It doesn't creep up in the news, and that's because you can never really tell if you can never really actually test all the different ways that you could change the input variables to a model. Right? So when we ran our experiments, we looked at credit scoring models that we built on different data sets, and we built them in a way that practitioners would build them. So these are models that perform well, that you could possibly use maybe to approve and deny loans. And we tried to use like the most conservative assumptions about how people could change their variables. So things that are physically immutable, we'd say you wouldn't be able to change them. These interactions between variables, they were just a property of the encoding. So if you took, for example, something like customer type and you coded Demley variables, like switching one on would have to switch the other one off. So under these cases, these are all constraints that we could agree on would really constrain the way you could change your input variables. And we discovered that a lot of people who are denied with fixed predictions. The number will vary based off the model that you're using, who you are, and what your input variables are. One thing that I think is particularly dangerous in this case is just the fact that people are still able to change their input variables, but regardless of how they change them, they will always be denied. And I think this is particularly dangerous because you could always tell someone a way to improve their score, but that score is never going to get good enough for you to be approved. So a broader implication of all of this is really this effect that we maybe call reasons without recourse. It's this idea that you can explain a prediction and tell someone how they could improve their score without necessarily leading to a better outcome.
Very interesting. That is exactly what I want to talk to you about in my last question and summing this up, namely the policy implications of your work and also how explainability relates to that. What should we take away from your findings? Who should be taken accountable for delivering non-fixed predictions?
I think there's a lot of machine learning researchers, for example, in responsible AI, who would be interested. just because this is really this mechanical, technical task that involves software development, that involves interesting math and computer science, and where they can design stronger, faster tests and better software to really be able to detect an effect that could lead to harm. So that's maybe one community that I think has access to like a research problem that I would say would lead to impact. From the policy angle, I think this idea that models can assign fixed predictions, it's something that we didn't know about, but that now we do. And it's an effect that we can kind of test for and that we could potentially fix, right? So in general, it's hard to get models that will always assign predictions that are responsive, so predictions that you can change. But at the very least, you could notify someone that their prediction is fixed and prevent them from having to reapply. So kind of maybe to motivate this, there is one story that appeared in the Financial Times like 2 years ago about a lady in the UK who was waiting on a liver transplant. And in the UK, these decisions are made with an organ transplant score. So she's waiting for 2 years. She should have gotten a liver by now. She looks into it in more detail. She finds out these decisions are made with a score. She goes to her doctor, and they together can find this score. It's online. And they start, fiddling with the input variables to try to see, okay, well, is she going to get a score to be approved? And they find out, like, regardless of how you change it, right, there is really no way that she's going to get a score that's high enough to ever qualify for an organ transplant. So this is really the first example that I've seen in the news about people being denied with a fixed prediction. And it required a lot of things to kind of work out to kind of see, right? The model had to be available. People had to be able to try around with it. And I think it's an interesting example because, for example, there is no right for this person to get the organ transplant. It's okay to be denied, right? But if at least like we notified them and told them that there was a very low chance that they would even get approved in the future, that would have changed their expectations for 2 years. It would have changed possibly their treatment path. There is just inherent value to transparency. Beyond that, I think it is possible to create models that will assign responsive predictions. It's just something that requires model development. So it's not just a quick fit and get the model and it works. But it's also the type of thing that, for example, is interesting to the research community and a challenge that we can build on. Last part was, I think, policy. There is room to have kind of meaningful consumer protection by just testing for fixed predictions. So this is something that like people who are developing these models in consumer-facing applications could do with internal tests. An auditor could also do it with access to the model. Once you deploy the model, you could do it for every person that it's predicting on. So you could really kind of apply this test at different points of the machine learning lifecycle and detect whenever the model is assigning a fixed prediction. And part of the reason why I think we spent so much time trying to develop the software is to build the foundation to be able to make that a reality, right? Like people are not going to be able to use a machine learning model unless there's software that's going with it, and unless it's kind of easy to use in the first place. This, I think it's worth saying, is just maybe one small part of consumer protection, but it's a type of thing that you could test easily and avert harm. And that's harm that's happening that I think would occur in a lot of different applications and could affect a significant number of people.
Thank you so much for being here with us today, Berk. We are looking forward to your future contributions.
Thank you for having me.
And to our viewers, thank you so much for joining, and I'm looking forward to see you in the next one.